extracting entanglement. It's about extracting entanglement from the quantum vacuum. So I will begin by talking some properties about the vacuum. The vacuum has physical properties. It has mechanical properties because of the Casimir-Polder effect. It has also thermal properties, as the Unruh-Hawking effect put into evidence. And it also has entanglement content. We can write a vacuum mode or vacuum state of some mode of the field in this manner. So we see from this that the vacuum is an entangled state between two disconnected regions. In the case of the black hole, we have that the vacuum state is an entanglement state between the modes outside and inside the black hole. In the case of the Rindler spacetime, we have that it can be expressed as this entanglement between right and left modes of the Rindler wedges. And there are many literatures that put into evidence this entanglement content of the vacuum. So the idea is that we can extract and transfer this entanglement from the vacuum to a pair of qubits. And I am going to present to you these results about this process in the cosmic string spacetime. So the cosmic string is a topological defect. It's an analogous to the Abrikos subvortices, and it can be generated in the symmetry breaking phase transition in the early universe as the Higgs mechanism. But the more important for us is that this spacetime has flat geometry, but not trivial topology. So this is the principal ingredient that we are trying to explore here, the non-triviality of the topology of this spacetime. And we want to know how this non-trivial topology contributes to the harvesting entanglement. This non-trivial topology will put into evidence by this angular deficit in the cosmic string spacetime. This angular deficit depends on the energy density of the cosmic string times the Newton's universal constant. So in this spacetime, we're going to quantize some quantum field. In this case, we're trying some scalar field. And we begin with this is not working. We begin with this metric that is just the Minkowski metric in cylindrical coordinates. But for the cosmic string, we have that this variable, this angular variable, it goes from 0 to 2 pi times b. This parameter b is not 1. It has an angular deficit that depends on the string. And in this metric, we can solve the wave equation and find the field modes. This depends on these Bessel's modified functions, and they have plane wave in the z direction. And with this mode, we can construct the green function of the theory of the scalar field by this expression. But we have to consider some characteristic of the cosmic string that we have to make some quantization condition over this string. We have to set this parameter 1 over b as a natural integral because of this is a necessary condition to avoid the radiation of a stationary charge in this spacetime. But with this condition, we can write the Weitman function of the scalar field in this manner. It's a finite sum of the Weitman function in the Minkowski spacetime, but with some angular displacement here. So we have now the cosmic string spacetime. Over this, we have the quantum field that coupled to this geometry. And over this field, we are going to analyze the dynamic of a pair of qubits coupled to the scalar field. So this two-qubit system will have this Hamiltonian. This is the free pair of each qubit separately. This is the first qubit. Each qubit is just a two-level atom. But in this article, we also consider this interaction term between the qubits, and we claim that this little interaction between the qubits will increase and benefits the harvesting entanglement process. This the J coupling constant refers, and these terms refers to the possibility of one qubit going up, while the other goes down, and vice versa. And this term is equivalent to the Heisenberg XY interaction in magnetism. The energy level structure of this two-level system is this. So the J coupling constant will separate these energy levels. So we now have energy states that are entangled, naturally entangled. And we will couple each of these qubits to the scalar field. And we use the usual manner of coupling Unruh-Levy detectors to a quantum field. We consider a monopole operator that depends on the internal structure of one qubit times the field evaluated at the qubit position. Okay. And this is the usual Unruh-Levy detector. But the main importance of this coupling is that they are sensitive to the vacuum fluctuation, because if we expand the field, we can see from this coupling that we have two kinds of processes. This pair of processes are real processes where the qubit goes up by absorbing some quantum of the field, or goes down by emitting some photon. These are real processes that conserve energy, but there's the possibility inside this coupling of virtual processes that do not conserve energy, and the qubit goes up by emitting some quanta, or going down by absorbing. This kind of process together would fill the vacuum fluctuation, and this is the main result of Unruh. This could serve as a thermometer of the vacuum state, and would prove the Unruh-Levy the Unruh effect. Okay. So we have a pair of qubits coupled to a massless scalar field, and the evolution of the whole system will be given by this Liouville equation in the interaction picture. And we are considering here a perturbation theory. We expand this in a Dyson series, and we suppose that in the initial time, the state of the field is the vacuum state, while the state of the atoms or qubits is some density operator that has no entanglement. And we have this final energy density operator of the whole system, of the total system. But we are interested only on the atomic part, on the two qubit system. So we made a trace over the field degree of freedoms, and we obtained the density operator, reduced density operator associated to the qubits. And this is the final result. We have that the final density operator will be the initial density operator, but plus some corrections in perturbation order. Here there's some matrices, and G plus is the Weizmann function of the scalar field evaluated at the qubit's position. But this procedure that we are making is only valid for with coupling constants and small times. So we are going, the laser is not working, but we're going this way. We solve the joint system, the total system, field plus 2 qubits, and then after that, we've made the trace over the field degree of freedom. But there's other possibility. We can make over this Liouville equation a trace over the field degree of freedom and obtain this master Limbrad equation for the density operator of the qubits. And after that, we can make the solution, resolve this master equation. But in both cases, we must to be some hypothesis with coupling constant. Typically here, we have to make some numerical methods. But the main difference is that the validity of this second procedure is for large time regimes, because we need some equilibration process, and the other approach is valid for small times. So the small times approximation is what we are showing here, and this is the result. This is the initial density operator of the qubits that has no entanglements. And after the interaction with the quantum, the vacuum fluctuation, we have that each of the matrix elements would be corrected by some terms. There are some population corrections, but there also appear some coherence terms outside the diagonal. And we measure the amount of entanglement in this final state. We use the negativity measure, and this negativity would depend on all the parameters of the system, the interaction time, the energy gap of the qubits, of the J coupling constant that we are considering, of the initial probability P of the states. Also on N, that is the topological charge of the cosmic string, and also on the spatial position of the qubits. There are many possibilities to choose the two qubits static in this space-time. We consider these three cases. And here I will show to you this case, some results about this axial case where the two qubits are parallel to the cosmic string but have an axial distance delta z. And the first result is this. After some initial time, there's no negativity. But there occurs a sudden burst of entanglement after some amount of time. And then the negativity grows with time linearly. But these results are only valid for a small time, so we cannot let the time to go to infinity because of perturbation theory will break down. But here we can see that this end is the topological chair of the cosmic string will improve the amount of entanglement. So when we have more topological chairs, we have more entanglement in this space-time. So the topology is benefit for this process. And also we can see that the direct interaction between the two qubits because of this Heisenberg XY interaction is good for the process of extraction entanglement. We see that the negativity has two maximum values at these points when the coupling constant J is exactly equal to plus or minus the energy gap, W. So we have this kind of resonance between the interaction coupling constant and the energy gap. And we see these maximum peaks of negativity. And we also see that the topological chair will increase the amount of negativity. With respect to the qubits location, we can say that as the separation between the qubits goes far, the negativity goes down in an oscillatory wave. Okay. This is for the case when we do not have direct interaction. J is equal to 0, so it oscillates and tends to 0. There's no final negativity when the two qubits are far apart. But we can analyze also when the two qubits go far apart from the cosmic string. So in this case, the entanglement also decreases in an oscillatory wave, but it tends to a finite amount of entanglement um, that is finite because we are considering here a non-zero J interaction. So this, if we consider J equals 0, this will oscillate and tends to 0 also. Well, this is a final plot. We have this here that the time and the distance between the qubits, and we show that outside the line cone between the qubits, we have no null negativity, so the harvesting entanglement is a non-local process. Okay, and this would be the conclusions. The vacuum can be thought as a natural source of entanglement, but it's a very small amount of entanglement because of the values we obtained. This Heisenberg interaction between the qubits is good for the harvesting process, and we have maximum resonance, maximum entanglement at these resonance points, J equal plus minus W. And in the limit of J equal different from 0, and when the two qubits go far apart, we have a finite amount of entanglement. And also the topological chair is increase the value of negativity and entanglements. Well, okay, that's all.
Okay, so questions?
Can you show the slide where you define this negativity?
Yes, here?
Yeah, thanks. I mean, like, let's say that, you know, think like you're an experimentalist and you have two qubits, like a spin state going up is 0. What is this exactly? You know, let's say spin up is 0 and spin down is 1 or something like that. Is this a correlation between two spins? Or like, or what? Because my question is this really an observable? Is this really an observable that you can do? You need an ensemble to measure it, right?
Well, the negativity name is because the appearance of some negative value of the in the partial transpose of the operator. But I don't know if it has a physical interpretation. How? I don't know.
I mean, you have a quantum computer with two qubits, and you can read the value of the qubits. How do you measure the negativity? That's the.
We need, first of all, the density operator and make the partial transpose over it. Or maybe this is a good entanglement measurement for a single two qubits, a pair of two qubits. For a more complex system, I don't know if it could be applied.
Okay, thanks.
Okay, we have time for one more question.
Hi, thanks. Do you have any intuition as to why the bigger topological charge gives you more harvested entanglement?
I a physical intuition about that. I don't really know. In almost all the cases, this happens.
Not disputing the result, but
Yeah.
just wondering what the intuition is behind it.
Yeah. It may be related to this expression of the Weidmann function. here, because the topological chart is related to the angular deficit, and it depends. It could give us the number of copies, if you like, of the Minkowski-Whiteman function. So when we have more topological charts, there would be more terms in this sum, and we can increase the correlation between the two qubits because of we have more correlation terms between the qubits.
Okay, so I think we have reached the point. So let's thank our speaker again.
Thank you.
Okay, so just to confirm, Partha Nandi didn't arrive during the Enrique's talk. Okay, so we finished.
Yeah, guys, a quick announcement. Tomorrow we'll take our conference photo, so don't miss that as well, right? And you had the email about the conference dinner for tomorrow, right? You got email, right? Okay, so.
I will probably take people from the reception at like 6:30 or something.
Yeah, trust him to drive in there.
It's a walk.
Yeah, it's really close. It's really close. Yeah.
Okay, so we finished the afternoon session.